We're going to keep on going with some more forces scenarios with you guys, with the electric fields and subatomic charges and stuff like that. So here we have a Q1 of negative 0.72 microcoulombs, 185 nanometers away from a proton, and the proton is 120 nanometers away from a second charge. And we are going to find out charge number 2, and we are going to say that the proton here has got a net force or total force on him. Let's say the net force on our proton is 0.0076 newtons towards the right. So we are going to try and find out what the value for our second charge is. Okay, well, let's just start with one thing at a time. We can find the force from Q number 1. So force from Q number 1 would be KQ1Q over radius 1 squared. So let's find the force for that one over there. And with that, we have 0.030 newtons, and the proton would be attracted to the left. So Q number 1 is attracting the proton with 0.03 newtons. Okay, so now I can figure out the force from Q number 2. Now, first of all, Q number 2 is actually winning because the net force is to the right, so I know that Q2 has a larger force than Q1 does. So first things first, it has to balance off force number 1. So first of all, we would need 0.030 newtons in order to just cancel force number 1. But not only is Q2 canceling out the force from number 1, it's also winning with another 0.0076 extra force, so to speak. So if I put those two together, it's got to be pulling with 0.0376 newtons altogether. So this has to be my force from my second charge, 0.03 newtons to cancel out charge number 1's force, and then it's winning by another 0.0076 newtons. So it's got to be pulling with that much altogether. And they're both negative, they're both attracting the protons, so that's what we got to use. So 0.0376 would be force number 2, so that would be equal to KQ2Q over radius 2 squared. The only thing I don't have is Q2, so we can solve for it. So take the 0.0376, multiply it by the 120 nanometer squared, divide by the K, divide by little q for the proton, and you'll have the big charge. So with that, we should get around 3.03 times 10 to the negative 7 coulombs. If we put it in the same notation as our Q1, that would be 0.303 microcoulombs, and it is a negatively charged particle as labeled up there, so charge number 2 should be negative 0.303 microcoulombs. Okay, and then again, like we talked about before, you could find the electric field over here. All you do is take the electric field would be that total force, that one right there, and divide by the Q of the proton. You'd have the net electric field at that location if you wanted to. Okay, so now I'm going to show you guys something else connected to forces. Let's take this scenario. Suppose we have, really simple, we are going to take a proton. So here's a proton, and here we have an electron over there, and we've got a proton and we've got an electron, and let's say they are 5.3 times 10 to the negative 11 meters apart. Let's clean that up a little bit. All right, negative 11 meters apart, okay? Or you can do 530 nanometers, doesn't make any difference. Okay, so I'm gonna start simple. I'm gonna find the force between these two guys. So what is the force between these two guys? You got the Q's, you got the radius. This is a pretty simple calculation. So we get 8.2 times 10 to the negative 16 newtons. All right, so that is a mutual force between the two. Now, I'm not sure if you guys realize what is special about a proton and electron separated by 520 nanometers. Well, if you're not sure, this is a basic hydrogen atom. One proton, no neutrons, and an electron. Of course, that electron is orbiting the proton. That's what happens in hydrogen. The electron goes around the proton, an average radius of 530 nanometers. So, of course, this is just like the gravity stuff that you guys did, where you calculated the force of gravity, and then you guys attached that to orbits. Well, you can do the exact same thing with this, because it is this electrical force, this Coulomb's law force, that is actually what's called, is actually creating the Fc for the electron as it orbits the proton. So for atoms and stuff like this, if you take this to the atomic level, if you look at atoms, this actually supplies centripetal force for the charge to go around, for the electron to go around, which means you could use this to find out how fast the actual electron is going. Because I can take that 8.2 to the negative 16, got the 8.2 times 10 to the negative 16, that's my electrical force. That is equal to good old Fc, or mv squared over r, and that would be the mass of the electron, because that's what's actually orbiting around. And then you can calculate how fast it's going. So use this, you got the radius, you've got the mass of the electron, you can find out how fast the electron is going around. And of course, now that I'm going to do this, I realize I can see an error they made here. This is not 530 nanometers. You know, sometimes you get going with things and something doesn't look quite right. Well, that didn't quite look right. It's because it's not 530 nanometers. It's 0.053 nanometers. Okay, that's definitely going to work out better, which means we got to change the force here. That force is not going to be to the negative 16 over there. So this, I believe, should be to the negative 8, which means this will be to the negative 8, but everything else should be good to go. All right, so then we can actually solve for it. Now we fix that slight little nanometer error, and then we can find out the speed of the orbiting electron. And that should give us a V of around 2.2 times 10 to the 6 meters per second. So that is how fast an electron would be orbiting around a proton if it was a hydrogen atom. Okay, so the same way we could use the force of gravity to find the speeds of orbiting planets, we can use Fe to find the speeds of orbiting particles around nuclei for atoms. Okay, so let's try something else with this to get a little more practice as well. Delete. All right. So let's take something actually similar. Let's take helium. Okay, so suppose we're talking about helium instead, and we looked at the electron going around helium. Okay, so let's even simplify. Let's say it's even going the same speed that we had for hydrogen. So let's say it's going 2.2 times 10 to the 6 meters per second around helium. Obviously, helium and hydrogen are they're not the same thing. You know, it's just one proton more, which changes the charge of the nucleus a little bit. But let's see what would the radius have to be for that, because obviously if helium has 2 protons instead of 1 proton, right, because there's 2 protons in the helium, there's going to be more charge, there's going to be more traction, it's going to pull it in. So let's even say it's going the same speed. What would the radius then be for that orbit for the helium electron? Okay, so let's see if we can sort of piece that a little bit together here. Now, this is what we were doing before. You know, we got the electrical force, and that electrical force actually creates the centripetal force, or the Fc. So those two have to be equal to each other. And we can actually just put them equal to each other. So you have the K QQ over R squared is going to be equal to the MV squared over R. And doing it this way is kind of nice, because then one of our radii will actually cancel out, and then we can solve for it. So we just have to flip those two things around and we will be good to go. So KQQ divided by MV squared would be equal to the radius of the path. And that's about it. Okay, so we have the k, the q, and the q, and we divide that by mv squared, and we've got the radius of the orbit. And so we put that in, we got the k, we got the q. Make sure for the big Q is 2 protons, so it'll be 3.2 to the negative 19. You got the charged electron, mass of the electron because that's what's going around, speed of the electron, and we would get a radius of about 1.04 times 10 to the negative 10 meters. Okay. So that would be the radius if it was going the same speed. Now, this is actually bigger than a hydrogen atom is, which is not the actual truth. We were just doing this question keeping the exact same speed and finding a radius. We'll sort of tune this up in a second. But helium is actually smaller than hydrogen actually is in terms of the first orbit, because of course helium has a second electron over here as well. But since helium has twice the protons, there's more electrical force. It actually pulls that electron tighter. This electron here is actually repelling the other electron, but it'd be the opposite side of the orbit, so it won't have nearly the effect as the 2 protons inside the nucleus. Okay, so that's the actual difference between the two. And of course, that 1.04 negative 10, that's not going to work out very well. Helium's actually smaller. So let's go with the actual real values, a little more accurate here. So if you take an actual helium atom, the speed of the electron for actual helium is around 4 times 10 to the 6 meters per second. So that's the actual approximate speed of an electron going around helium, and it has to go a lot faster than it did here, which is the speed we just copied for hydrogen just to practice. It has to go higher than that because since it is closer, it has to go faster in order to try and stay away from that nucleus. So if we did this and we did the calculation again, okay, so the radius would be, same type of thing, kqqq over the mv squared. It's the same derivation and combination as this. We can calculate the actual radius of, or approximate average radius of a helium atom. And so then if we put those values in, we get around 3.16 times 10 to the negative 11 meters, which makes sense because if you remember the hydrogen one, the radius of hydrogen, give or take, was about 5.3 times 10 to the negative 11 meters. So for the helium has more charge in the nucleus, so it pulls that electron tighter, so it makes sense that helium would have a smaller radius because it's got more traction to pull it in. But since the radius is smaller, the electron definitely has to move faster in order to stay away from the nucleus pulling it in. Okay, so that's how you can apply basic electrical forces to atoms and orbits and stuff like that. And it's the exact same idea as you guys did with gravity. You found the force of gravity and then you attached it to Fc to find how fast things could orbit in space and stuff like that. Same thing here, no difference. You can find the electrical force between a nucleus and electron and then calculate the speed or the radius of the path of it going around. And it's an easy way and a really common way to find out different quantities for subatomics that are orbiting.